Hi. So if you remember, before the spring break, we learned about Mercury and Venus. So we have a lot to learn about other planets as well. So let's move a little bit quickly. So by the assignments that I gave you over for the Monday and Wednesday, you learn about a little bit details about the Earth. But let's finish up with these PowerPoint slides. So these PowerPoint slides are available on Blackboard for you as regularly. So you may use those, and also you may watch these videos, and then as I cannot count your participation as regularly, like taking the attendance, what I'm going to do is you have to answer the questions following this video, and then those will count as your participation credits, as I mentioned in the Monday meeting. All right, so let's move on. So it's about Earth, and then we'll talk about Mars. Okay, so as you know, there are 7 naked eye solar system objects in the sky, which are Mercury, Venus, Mars, Jupiter, Saturn, and Sun. And the moon is the other one. And all of these names are associated with gods' names. Anyway, so Earth is the coolest planet that we know. And do you know that there are 13,000 man-made objects orbiting around the Earth? It's too much, right? So 13,000. So how can we count it even, right? So the man creating things even in the space that's disturbing the environment. Anyway, so even though we have that much amount, like 13,000, 500 of them are currently operational satellites. So mainly they are observing the Earth behaviors, right? Mainly it's observing the Earth climates. All right, so the basic characteristic of Earth, so we already know all these things, but roughly let's go over. So the average distance from Sun is 1 astronomical unit, which is 93,000 miles. And then the aphelion is 1.07 astronomical unit. Aphelion is the furthest distance from the Sun to the Earth orbit. And the perihelion is 0.94 astronomical unit. So perihelion is the closest approach to the Earth orbit, the Earth to the Sun. Then the eccentricity is the percent difference between these two. So how much difference is the aphelion and perihelion is. So currently Earth is not orbiting in a perfect circle. So it is 0.0017 eccentricity. Then the orbital period is 365.256 days. So roughly it is 365. So that's why we say, like, for a 1 year, there are 365 days, right? So this 0.256 adds up and add 1 day every 4 years. So that's a leap year. Then a solar day is 24 hours. The sidereal rotation period is 23 hours and 56 minutes, which is 4 minutes less than the solar day. And the albedo, the sunlight percentage that we are getting, albedo is 0.39. Then the escape speed on Earth is 7 miles per second, and oblation is 0.0034. So we know a lot about Earth, but we're going to minimize our time spending learning about Earth, but we will be touching the main points. All right, so orbit and rotation. So, you know, like orbit means, orbit means the Earth is going around the Sun in an elliptical path, as we know. And the rotation means the Earth is rotating around its own axis, right? Then we know that the Earth axis is tilted by 23.5 degrees. So this slide is about the seasons. So as you see here in this picture, the Sun is at the center, but this picture need to be edited a little bit. Sun should be a little bit closer to somewhere here, because Sun will be in one focus of the ellipse. I'm not going to go over this slide that much in detail. So December, we know, like for the northern hemisphere, it's the winter, but for southern hemisphere, it is the summer. In July, the northern hemisphere, we have summer, but for the southern, in Australia, some areas like that, it's southern. It's the winter time, right? So these climate, the seasons happen due to the tilt of this Earth axis. All right, so here, if you look at it closely, again, this picture need to be edited a little bit. So Sun should be a little bit closer here towards the location of Earth in December. So sun should be shifted this way. I should have used a different picture, right? Anyway, so the sun should be somewhere here. So that is, this location of Earth is the perihelion, which is the closest approach to the sun. Earth orbits is in a closest approach to the sun, and this will be the perihelion. I think I do have a different picture down here. So let's move on. Yes, so here it is the perihelion, and that's the aphelion. So let me go back. Even though this picture look like a sun is at the center from these two, but if you look at these numbers, it's a little different, right? So these are two different numbers. So it's not this, the Earth orbit is not in a perfect circle here. It is elliptical road. All right, so if you look at these numbers, this number is less than that number. So it acts against the seasons, right? So here it is the winter time. So we feel like we should be very close to the sun than in, I mean, further away from the sun than in the winter. Did I make a mistake? Okay, so we feel like in the winter time, we should be further away from the sun. Actually, if you look at these numbers, we are further away from the sun in the summertime. So these distances acts against the seasons. So seasons happens due to the tilt of the Earth. All right, so anyway, if you think about long-term climate changes like ice ages, right? So over the Earth's long history, there were dramatic changes in our climate. So ice ages has come and gone. There was a strong pattern that can be explained why ice ages happened when they do. So that's called the Milankovitch cycles, and the scientist Milutin Milankovitch is the person who described these cycles. So these long-term climate changes happen due to the eccentricity. So eccentricity means how much difference is there between the perihelion distance and the aphelion distance. So in the current model of Earth, as you see in this picture, the Earth is rotating somewhere in this orbit. It's not further away, right? So the current position of Earth is represented by this dashed lines, let's say. So long time ago, the Earth was orbiting somewhere here. So the perihelion and the aphelion differences are large. So we call this as eccentricity is large. So we get big climate changes like ice ages because we are receiving less sunlight when we are further away from the sun, right? So 100,000 years ago or 413,000 years ago, we had the ice ages because of this eccentricity. Anyway, so it is a little bit more complicated than I mentioned over here. So here, like if you think about the current situation, like current orbiting directions, then we are receiving 23% sunlight intensity differences in the current position. So it's when we are orbiting in this dash lines. But imagine like if you are further away, then we should get less sunlight than now, right? So there will be a large differences in the sunlight intensity. So as I mentioned, Milankovitch cycles are a little bit advanced than what I mentioned. So there are three things that involve with the Milankovitch cycles. Those are eccentricity, axial tilt, and the position. So here, I talked about the eccentricity. So that's the difference in the shape of the Earth orbital path, right? So here, this red color lines here represent the circular path. The purple color lines represent a elliptical path. So eccentricity, like if you think about today's eccentricity is 0.017. So that's the, from that, we get 14% closer to the sun and 31% more energy receiving from sunlight. We'll talk about the energy sources that we have in the next slides. But for now, let's think about just the solar energy. So we are receiving about 31% more energy with the today's eccentricity. But long time ago, when we have two different numbers, like this is a somewhat in the circular path, so the eccentricity is 0.0005. So that's make a big difference in the energy that we are receiving. And also on this one, it's 0.0067 eccentricity. So eccentricity is the variation of the energy that we receive from sun when Earth orbit is elongated than it does when Earth orbit is more circular. Then the second one is the tilt, as I mentioned. So currently we are in 23.5 degrees tilted, but this can be varying up to 24.5 degrees. So it can be 0. Actually, there's no record about having 0 tilt, but over the time, this tilt angle can vary from 20.2 degrees to 24.5 degrees. Now we are in a good condition, good tilt angle with the 23.5, and it is a good tilt that we can maintain our orbital speeds to have a good magnetic field going around us. So we are livable condition on the Earth, right? So here with the so the Earth tilt axis can be vary between 22.2 and 24.5 degrees. The greater the tilt angle is, the more solar energy the poles receive. So if you go 24.5 degrees, so it's tilted a lot. So if you imagine about this picture, so the northern pole is farther away from the sun, but the southern pole is going very much closer to the sun, right? So we will be receiving more sunlight if we have a more tilt. Then the other one is the precession. So if you think about a spinning top, so if you spin a spinning top with a little angle, then you will be seeing like it's start wobbles, right? It's creating a wobbly path. It won't keep that tilt as it is. It will be changing the position. So it will be counting to the eccentricity as well. So all these three factors are counting towards the Milankovitch cycles, and that's give the effect of long-term climate changes. All right, so please answer the questions below. So that will give you the participation credit for this part of the lecture.